I'm Michael Arthur.
I'm Nicholas Love.
And I'm Emma Webker.
And we're Team NEM.
The mission was to create an energy-efficient AEV for the National Parks Department, which would complete the mission. The mission was to start at this point, then travel up the incline and stop at the Grand Canyon stop. Here the AEV would pick up the passenger cart and travel back down the incline, around the curve, and stop at the Caribbean Waves. After stopping at the Caribbean Waves, the AEV would travel up another incline to the Alaska stop. After stopping at Alaska and allowing time for passengers to exit or enter, the AEV would travel away from Alaska and stop on the incline for a picture opportunity. Then the AEV would travel to another stop at the mountains. After this stop, the AEV proceeds to the next stop and then travels back up to the Grand Canyon stop. Here the AEV dropped the passenger cart back off and travels down to the maintenance station, completing the mission.
A supply box was given at the beginning of the design process with various pieces. Any parts not included in the box could be manufactured using the 3D printers in the classroom. Each team member made individual designs and communicated these through orthographic sketches after reviewing parts available from the AEV kit. My initial design was aimed at simplicity and aerodynamics.
My design prioritized weight, ease of assembly, and aerodynamics.
My design also prioritized weight, ease of assembly, and aerodynamics.
Each of these three designs were compared to a reference AEV in a concept matrix. This matrix gave a plus if the design listed in each column was better than the references, a 0 if it was the same, or a minus sign if it was worse in comparison. Each design was evaluated using the criteria seen to the left.
A concept scoring matrix was also created to evaluate these designs and allowed each area of evaluation to be weighted. Balance was weighted most highly, followed by center of gravity, aerodynamics, weight, and ease of assembly. Components from all three individual designs contributed to this group design, and the team design was crafted after deliberating together. The L-shaped arm was mounted onto a 2x6-inch piece of plastic, which held the Arduino board and battery. Two wings were attached at an upwards 45-degree angle, which held each motor. The group design, as well as all individual designs, used the EP3020 blades.
This first group design was used for preliminary testing of the code. Coding was conducted using the Arduino program.
The main obstacle with the code was consistently having the AEV stop. Simply cutting power to the motors did not immediately stop the AEV because the AEV would coast, so in early versions of the code, the motors were reversed and put at a high motor speed to act as a brake. This was of course very energy inefficient, and later versions of the code allowed the AEV to coast into stopping points, eliminating the need for reverse propulsion. In System Analysis 1, two different propellers, the EP3030 and the EP3020, were tested in the wind tunnel. This wind tunnel lab supplied data to plot the propulsion efficiency versus the advance ratio of each propeller in two different configurations. These two configurations were pusher and puller, or tractor, depending on which way the motor was mounted. The EP3030 propellers were concluded to be more efficient in terms of propulsion in both the pusher and puller configurations. This conclusion influenced the team decision to use the EP3030 blades instead of the EP3020 blades in future designs. To evaluate energy usage of various AEV runs, a MATLAB code titled System Analysis was created. After converting Arduino data to SI units, this code asked the user to create phases of each run, and would then calculate the energy usage of each phase using midpoint approximation of Riemann sums.
After testing with Design 1 on the test track, Design 2 was designed and constructed. This design focused on reducing the overall mass, as well as allowing room in the front for the servo motor. The EP3020 blades were swapped out with the EP3030 blades, and a 3D printed hook was designed to use to connect the AEV to the passenger cart by rotating the hook using the servo motor. The curvature of this hook was intended to create a good connection between the passenger cart and AEV, reducing the likelihood of a disconnection on the incline and curve, as well as increase the tolerance of the distance the AEV had to be from the passenger cart to connect. In theory, this hook would pull the passenger cart closer to the AEV and hook or push the passenger cart away and hook if too close. However, during testing, the team learned if the hook made contact with anything, this caused an error in the code. The total mass of this design was 235 grams.
From design 2 to 3, the objective was to become more energy efficient. The plastic piece where the servo motor sat in design 2 was removed and replaced with a 3D printed bracket for the servo motor. The hook was replaced with a bent paper clip which was lighter and thinner than the previous hook, making it less likely to hit the walls of the connection circle of the passenger cart. This final design completed the mission consistently after replacing the Arduino board and servo motor a few times due to faulty equipment. The final run used 506 joules of energy, weighed 230 grams, and completed the mission in 83.31 seconds. This made our joules to mass ratio 2,200. This project allowed each team member to gain knowledge in coding, design processes, and formal communication in terms of lab reports and memos. After completing the project, some design choices, such as not incorporating a mechanical hook using an additional servo motor, or switching entirely from our propeller-based design, seemed better. But as a team, we are proud of our design.